Good evening, ma'am. Our OSR for today is number 2. My problem is an equimodal liquid mixture of N-hexane, N-heptane, and N-octane shall be batch distilled at 1.5 atm. In order to recover 85% of the hexane, assuming ideal system, using the Priester chart for equilibrium constants and using mean relative volatilities, determine the operating temperatures, mole percent composition of products, and mole percent of the feed that is distilled. In this problem, in number 2, it is a batch distillation problem. So we make a basis of 300 moles. Our XFI is stated that it is equimodal. So we divide this into 3 components. For let A be N-hexane, let B be N-heptane, and let C be N-octane. So we are given a pressure of 1.5 atm. That's an operating pressure. So we also need to convert this to PSI A, since in the Priester chart it is in PSI A. Also, we are given the percent recovery of 85%. So ang required natin is the operating temperatures, which is T1 and T2, and also the mole percent composition of the products. So we have percent XW, percent XT, and also the mole percent of the distilled. So that's percent F. So the solution, we assume operating temperature initial startup of 224 degrees Fahrenheit. So I have assumed a while ago several trials, and we have assumed that 224 degrees Fahrenheit is the right, will yield an amount of 1.00. So for hexane, heptane, octane, we have the mole percent to feed, which is 1/3, 1/3, and 1/3. Ki is obtained using the Priester chart. So using the temperature we have assumed and the pressure that is given, we can plot this in the Priester chart. So here. So in the handbook, we use 224, so about here, and at pressure of 22.05 psia, we will obtain values for N-hexane, N-heptane, and N-octane. So with that, we obtain values of Ki of 1.77, 0.82, and 0.41. We get the YFI by simply multiplying XF and Ki. We get 0.59, 0.2733, 0.1367. If you add all those, the summation of YFI, we get a value of exactly 1.000. So that will be a good assumption for this one. Now we assume a value for T2, which is 248 degrees Fahrenheit. Also, we do, using the Priester chart, we also use this value. So 248. So with that, by plotting it 248, we get values for Ki with the nomograph at N-hexane, N-heptane, and N-octane. So we get values of 1.77. We get values of 2.38 for hexane, 1.12 for heptane, and 0.59 for octane. And we get the XW of 0.1253, 0.3445, and 0.5302. Then to obtain YWI, we simply multiply XW and Ki. So we get 0.2982, 0.3858, 0.3128. And then if you get the summation of YWI, you get 0.9969, or almost equal to 1.00. Once you obtain the values for respective K's, K, for temperature 1 and temperature 2, we get the alpha AB1 and alpha AB2 by simply dividing Ka over Kb, and the other one for alpha hexane octane for Ka over Kc. We all have the values this for this alpha to be obtained. So using the K1, which is 1.77 over 0.82, we get a value of 2.1585, and the value for alpha hexane octane is obtained by dividing 1.77 over 0.41. We get a value of 4.3171. For alpha 2 hexane heptane, we divide 2.38 over 1.12, we get 2.125, and we divide 2.38 over 0.59 to obtain 4.0339. So once you get alpha AB1 and alpha AB2, you simply get the product of those two and you get the square root to get alpha AB mean. You also do the same for alpha AC to obtain alpha AC mean. So by doing those, we get a value of 2.1417 for alpha AB mean and alpha AC mean for 4.1731. Using the Rayleigh equation, which is ln Wx over x fxf is equal to alpha mean times ln of Wx over Wi over fxf, we simply substitute everything in the equation. But first we have to get the value for Wx, Wa. So in order to get that, we use the percent recovery, which is 0.85. Percent recovery is equal to dxda over fxfa. So you get these values. F is given for hexane is 100, xfa is 1/3, percent recovery is 0.85. You get dxda, which is equal to 0.85 times 300 times 1/3. That will yield a value of 85. Then we substitute it in the equation. Fxfa is equal to dxda, this is material balance, plus Wxwa. We have value for dxda, fxfa. We don't know the value for Wxwa, which we will use in the Rayleigh equation. We will obtain a value of 15. Once we get Wxw, which is this one, we can now use everything in the equation to obtain the unknown, which is Wxwb. So using shift solve, we will obtain a value of 41.2384. We also do the same for Wxwc. We have everything in the equation. We substitute alpha AC mean here and fxfc. So we also use shift solve to obtain the value of Wxwc, which is equal to 63.4697. So we will need to obtain W, which is equal to Wxwa plus Wxwb plus Wxwc. It will yield a value of 119.7081. And for this equation, material balance of F is equal to D plus W. We have W, we have the feed, 300. W is 119, we obtained a while ago. D will be equal to 180.2919. So we use this equation once more to obtain our respective XDAs. So for hexane, 100 is equal to 119.7081 times 0.1253, which is a W here, and XWWI is 0.1253 plus 180.2919 times XDA. We shift solve our value of XDA. We also do the same for heptane and octane. So we just replace the XW and the ito lang pala, sorry. So we will obtain the value for XDB, and also for octane we get XDC. So once you get the XDA, DA, DB, and DC, we multiply it by 100 to get the percentage. So in the mole percent product, we get 47.15% for hexane, 32.59% for heptane, and 20.26% for octane. So that is the percent XT. For percent XW, we just divide WXWI over W times 100. We have W, we have WXWI. For we have this one, and this one. We just divide it by the W, which is 180.2919. So wait, I mean 119.7081. So once we do that, for hexane we get 12.53%, and for heptane we get 34.45%, and lastly for octane we get percent XW of 53.02%. For the last required, we get the mole percent distilled in the product, in the percent in the product distilled. So percent F is equal to D over F. So we have D, we have F, so which is 300. D is 180.2919. We multiply by 100 to get the percentage. So doing so will yield a value of 60.1%. So that is how you solve for this problem in OSR for number 2. Thank you.